And we're going to be talking, we already talked about pressure, and we've talked about buoyancy, and we talked a little bit about this, but um, we didn't talk too much. We talked basically what the idea of pressure is, but like being under a fluid, the difference between gauge pressure and actual pressure. But we're also going to have to talk about flow rate, something known as Pascal's principle. And finally, Bernoulli's principle. So we've covered this. You know the definition. Pressure is defined as force over area. And you know that it can be measured in things like PSI, atmospheres, torr, and there's even another one that I didn't bring up because it's really only used by like meteorologists, millimeters of mercury. Have you guys ever heard of that one as a pressure measurement? I don't really know how it works at all, but I know that if you look on any weather app, they'll give the pressure in millimeters of mercury. So, and then of course, what we're going to use, the Pascal. There's also, we talked about buoyancy, which is the force on an object that is under a fluid. So we know that the force itself, which is the buoyant force, is the weight of the fluid displaced. So it's the density of your fluid, the volume of your object, and g. We talked about what pressure under a fluid is, and we talked about the difference between gauge pressure and actual, but that was about it. Today we're going to have to do a little bit better, okay? So we're going to talk about all three of these today because they're all just fairly straightforward topics, but these last two are where the meat of this unit is. So I want to try and make it to the point where we've been able to talk about both of them, but we won't do any actual practice stuff until tomorrow, okay? So let's start by talking about a fluid first. And to do so, I want you to consider something like a swimming pool. I don't know if it's big or small. There's no scale. I mean, if this is you, I don't think it's a very big swimming pool. But if this was you, well, maybe it is a big swimming pool. Okay? So which kind of swimming pool do you want?
Maybe like in the middle between those two.
In the middle between those two?
Yeah.
All right, so
Yeah.
you can't reach the bottom with your head above the surface. You're okay with that? Do you know how to swim?
Yes.
Okay, so we're good. So here's how there's two different things when it comes to fluids and dealing with pressure. This is going to be static pressure, meaning the fluid isn't moving, right? So you have a tank like this. So even if there's a current, we tend to call this a static pressure, in that the idea is the fluid isn't moving very much compared to the person that's in the water. When fluid begins to move, our ideas of pressure have to change a little bit because the movement of the fluid affects the pressure. So we're talking about pressure in a static environment where the fluid's not moving very much. And basically, the idea is pretty simple, that when you're underneath the fluid, there is a whole column of that fluid above your head. And it's pressing down on you. In fact, that's what causes the pressure when you're underneath a fluid, is the fact that the weight of this fluid is pressing down on top of your head. Now, pressure acts everywhere, so something to consider is that if there's the pressure that might be at the top of your head when you're standing at the bottom of the pool, but there's pressure against your legs too, and it's based on the water that's, all stacked up in here. So the deeper you are, the more pressure you're going to feel. But let's just talk about basically where this comes from. Again, it comes from the weight of all of this fluid. In the pool, that would just be water, but of course, you could be under salt water. Salt water is heavier than fresh water. So if you're at the same depth in salt water than you were in fresh water, you'll experience more pressure. But if you were like under Jell-O, you'd experience even more pressure because Jell-O has a higher density. It weighs more. So we'll start off by saying that the pressure that they experience comes from Well, the definition, force divided by area. So this area would be the cross-sectional area of the object. So if this was Emery, it'd be, if we're talking about the pressure on her head, it'd be the cross-sectional area of her head, or maybe the cross-sectional area of her body. And this force is the weight of the fluid above you. And this is what's known as the gauge pressure. The pressure your pressure gauge would read. Okay? Now, obviously, we'd like to see if we can find a way to express this that has something to do with the fluid. So we're gonna start messing with this, okay? We're gonna put some new stuff in there. Like, for example, the gauge pressure, I could write this as the mass of the fluid above you times G. That would be the weight of the fluid above me in terms of the mass of the fluid divided by the cross-sectional area of the object. But just like we did the other day, the mass of the fluid will depend on the density of the fluid, right? A denser fluid would have more mass than a less dense fluid. So I'd really like to express this in terms of those properties, because a lot of stuff that has to do with fluid dynamics is based on it's based on density, and I'd like to kind of express this in terms of the density. So one way to do that is to remind myself that the mass of the fluid divided by the volume of the fluid would equal the density of the fluid, right? Density is mass over volume. That okay? So what I want to do is find a way to write the volume of the fluid. Now I drew it like a cylinder, and you guys know that the volume of a cylinder is what? No, you're thinking of a cone, but you're on the right track. Go ahead. Pi r squared times the height. So if this is the height, and I wanted to know what the volume of that cylinder is, it would be pi r squared times the height would be the volume of the cylinder. Unfortunately, Emery's not really a cylinder. Her head's roundish, but she's got the shoulders in there and stuff. So we can replace pi r squared with just her cross-sectional area times the height. That would be the volume of the fluid. You guys see what I'm saying? Pi r squared is the cross-sectional area of a cylinder because it's round. So if I just used Emery's cross-sectional area, I would suddenly have the volume of fluid above Emery. That okay? So let's put these things together and say that the density of the fluid would equal, I'm sorry, not the density of the fluid. What am I doing? The mass of the fluid would equal the density of the fluid times the volume, but instead of volume, I'm going to put the area of the object, the cross-sectional area, times the height. Do you see all the things I'm putting together here? And you see why I'm putting them together this way so far? Because I'm going to replace this m in just a minute. All these things together, so we'll get pressure, the gauge pressure, is going to equal density of the fluid times cross-sectional area of the object times the height of the column, all divided by, times G, all divided by the area of the object. Right, just substituted it in. And it's clear the area of the object cancels out, doesn't it? So we get the gauge pressure equals rho G H. Right, in a slightly different order because this is the order of the letters on your equation sheet. Now, H really represents your depth. Although we described it as the height of the column, it's your depth under the fluid. Okay? Does that make sense to you? Because it's this H is how far down you are from the surface of the fluid. Okay? So you might see this written as with a D there instead of an H for depth. I'm going to leave the H here because that's what I think what's on your equation sheet. But it just has to be how deep under the water you are. Now, I want you to remember this is a pressure. It's not a force directly. It's the force divided by the area. So if you wanted to know what force you're experiencing, you'd have to multiply this by the surface area of your body. That would tell you how much force you're experiencing. But also keep in mind, it is depth dependent, which means the pressure experienced here isn't as great as the pressure experienced there. The deeper you go, the more pressure you experience. Since your feet are lower than your head, or at least in this picture they are, there'd be more pressure on your feet than your head. And this isn't necessarily a small difference. It can be a very large difference depending on how big you are and how dense the fluid is. But remember, that difference in pressure is acting all around you. So anything that's in contact with the fluid is experiencing that pressure. And so the pressure is getting smaller and smaller towards the top, but bigger and bigger towards the bottom. This creates the buoyant force, the fact that there's more force on the bottom than there is on the top. That's what's buoying you to the surface. We already talked about what the buoyant force is, but it comes from pressure, the pressure of the fluid above you. And now we know the pressure is height dependent or depth dependent. Now, this is called gauge pressure because it only includes the weight of the fluid above you. But the truth is, and I know you have a hard time visualizing this, and I think I have a way of helping you with this. We are under an enormous amount of pressure from our atmosphere. I mean, how high is the atmosphere? Pretty high. That narrows it down. Do you guys have any idea? It's several miles, about 120,000 meters. So it's way up there. I bring that up for a couple of reasons. One of the most important one, a couple 120,000 like feet. I said meters, feet. I bring it up only because air might not feel like it weighs very much, but there's a column that's 120,000 feet above your head of air pressing down on you. One atmosphere is actually a lot of pressure. That's the only reason we're capable of breathing. I know you think that you are pulling air into your lungs, but that's not what's happening. When you inflate your chest, air pressure is pushing it into your lungs. That's coming from the outside. That's how all vacuum cleaners work too. There's no vacuum. There's just an opening of the volume and the air pressure fills it in. It's an incredible weight. So we don't include it generally when talking about like how much pressure am I under when I'm under the water, because we live under that pressure all the time. But gauge pressure is just the fluid above you. It doesn't include the atmosphere. Actual pressure is the pressure of the atmosphere plus the gauge pressure. That would be actual pressure. So pressure of the atmosphere plus rho GH. That's actual pressure. So if you're a diver, you only have gauge pressure because you only need to know what the extra pressure is on you. But if you want to know what the actual pressure is, you have to include the weight of the atmosphere too. Good so far? All right. Next thing, because all this works together, and we're not going to do a whole bunch of practice questions about what's the pressure on you when you're underwater. That's just plugging in equations. Yeah. What we're talking about here is something called flow rate. And let's talk a little bit about flow rate today. This is changing. What we were talking about before is about static fluids. We're going to talk about something more dynamic this time. This is how fluids flow and some of the characteristics of them when they flow from one place to another. We transport fluids all the time, right? You have hoses and you have pipes and stuff like that. This is how your sprinkler system in your house is designed to work. You may not have to work on it, but I work on mine all the time. Someday, I hope you will own a house, and someday, I hope you can fix it yourself. Because trust me, I can't tell my story because we lost the 2 minutes I needed to let you know something, but when this volume makes it to the place that's skinnier in the pipe, you understand that volume is going to have to spread out in the pipe. because the volume has to stay the same. The volume of water is not changing. So this is known as Pascal's principle, that the volume flow rate stays the same. The implication is the velocity of the fluid here is going to be way smaller than the velocity of fluid here, because that fluid has to move faster because suddenly it's a lot longer inside the pipe. The way this looks is the cross-sectional area of the big section has a velocity that is slow, while when you get to the small cross-sectional area, the velocity is fast. The smaller you make the opening, the faster the fluid is going to flow. That is Pascal's principle. I wrote it with big and small, but we could write it as A1V1 equals A2V2, where this is cross-sectional area and this is velocity. That's known as Pascal's principle.